Moths have evolved to absorb the maximum amount of light in order to see in the dark, and researchers are using this technique to create solar wallpaper. The paper-like panels will be designed just like a moth's eye, with microscopic patterns to gather ambient light towards the center to produce ultra-thin flexible solar panels. This technology will be used in energy production and powering smart sensors. It has also shown to enhance light absorption by 90%, says researchers. The University of Surrey began their research using graphene, a material that is only 1 atom thick, and although flexible, the carbon-based material was inefficient in absorbing light. Keeping the graphene as the base, the team looked at nature to see how certain animals see in the dark. Nature has evolved simple yet powerful adaptations, from which we have taken inspiration in order to answer challenges of future technologies, explained Professor Robbie Silva, head of the Advanced Technology Institute in a recent press release. After combing the animal kingdom for a lead, the team discovered moths' eyes have microscopic patterns that allow them to see at night. By gathering the light towards the center of their eye, moths are able to eliminate any reflections and avoid making themselves known to predators. We have used the same technique to make an amazingly thin, efficient, light-absorbent material by patterning graphene in a similar fashion, explained Silva. Graphene has already been noted for its remarkable electrical conductivity and mechanical strength. Professor Robbie's team understood that for graphene's potential to be realized as material for future applications, it should also harness light and heat effectively. Solar cells coated with this material would be able to harvest very dim light, said Silva. Installed indoors, as part of future smart wallpaper or smart windows, this material could generate electricity from waste light or heat, powering a numerous array of smart applications. New types of sensors and energy harvesters connected through the Internet of Things would also benefit from this type of coating. Dr. Jose Anguita of the University of Surrey and lead author of the paper commented, as a result of its thinness, graphene is only able to absorb a small percentage of the light that falls on it. For this reason, it is not suitable for the kinds of optoelectronic technologies our smart future will demand. Nanotexturing graphene has the effect of channeling the light into the narrow spaces between nanostructures, thereby enhancing the amount of light absorbed by the material. It is now possible to observe strong light absorption from even nanometer-thin films. Typically a graphene sheet would have 2 to 3% light absorption. Using this method, our ultra-thin coating of nano-textured few-layer graphene absorbs 95% of incident light across a broad spectrum, from the UV to the infrared. The next step is to incorporate this material in a variety of existing and emerging technologies, said Silva. We are very excited about the potential to exploit this material in existing optical devices for performance enhancement, whilst looking towards new applications. Through Surrey's EPSR-funded Graphene Center, we are looking for industry partners to exploit this technology and are keen to hear from innovative companies who we can explore the future applications of this technology with us.